So in the second part, I'm going to talk about functors, natural transformations, and adjunctions. And you need the first two you need this one to understand what this one is. You need this one to understand what this one is. And adjunctions are what give monads. So I think people have heard this term. I don't know how many people have heard natural transformations. Some have. And then adjunctions are what a lot of people consider adjunctions to be what makes category theory, or the real new edition of category theory over older math. So, and then the final block, I'm going to talk about monads and the Kleisli category and endofunctors, initial algebras, maybe terminal final coalgebras and stuff like that. And then finally, I was going to talk about monoidal categories, except that I think that that's not as relevant as I thought. So I like it, and I think it's relevant outside of functional programming, but I think it might not be as relevant. So my thought was what I would do for the third is ask you about halfway through to, in groups, talk about things that you might want to know more about. And then I don't know, really quickly if we can, I don't know if this is going to devolve, but try to get into a list of some things. Within 10 minutes, have a list of things that we can do for the last 40 minutes or something. So if you don't like that idea, tell me during the second break, or if you do like that idea. But start thinking about which topics in here are those you'd like to see expanded upon. So either because you want more clarification, you want more examples, or you want to just go deeper into the math or the whatever. So the first thing we'll talk about is functors. And if you know what a functor is from category theory, then you already know this. If you know what a functor is from functional programming, I think you're thinking of a functor from Haskell to Haskell. If you're always working within one category, Haskell, then functors and monads and stuff like that are just go from you to yourself, kind of like a monoid. It's just this one world I live in, and then I go between it to itself all in different ways. So I have functor class that takes an object, gives back an object, has a kind of F-map type mapping thing, and has some properties. And so that's what a functor may be to some of you, if my understanding is right. But functors really go between two different categories, where those two categories could be the same one. So let me define what a functor is. We've got a bunch of categories so far. We've got every set gives you a discrete category with no morphisms between elements. There's the category of sets. There's a post set is a category. The elements and an arrow if A is less than B, there's an arrow from A to B. A monoid is a category with one object where it's just you have int and you have all functions from int to int, and you can follow them around and stuff like that. Now we're going to talk about maps between categories, and that's what a functor is. So definition, let C and D be categories. So you already have these two categories. Maybe they're the same one. Maybe they're both set. Or maybe they're both Haskell. A functor from C to D, F from C to D, is written in the same kind of notation as we wrote functions. F colon C arrow D, but it consists of more stuff. First of all, it consists of a function from ob C to ob D. Every object in C returns an object in D. And the notationally nice way of writing this might be ob F, because it kind of has notational niceness to it, because F goes from C to D, so ob F goes from ob C to ob D. But it gets kind of tiring, so people overload the symbol to mean I can use F to act on objects. And they use the same symbol to write what it does on morphisms for every C1 and C2 in ob C. So if you have two elements in two objects in C, then you have a Hom set. So you have C knows what you mean by a morphism from C1 to C2. And it has all that whole set of morphisms. So this is a set right here. And if I want to give you a function, I give you another set and a function. The other set is going to be Hom in D from F of C1, because F can apply to an object to F of C2. So after I'm done writing this definition, we'll do the example of some examples from Haskell or something. I could write Hom F here. Like maybe someone might want to write Hom F, taking Hom C to Hom D. But I prefer notationally, it just gets heavy, so I would write F from C to D. I'm overloading F. It can act on objects or it can act on morphisms. And so a category has 4 pieces of structure. It has a bunch of objects, has a bunch of morphisms, has an identity, and it has composition. And F so far is working on the first 2, the objects and the morphisms. But the rules for functors act on the second 2 in some sense. The rules are that for any C in ob C, if I look at the F can apply to IDC. IDC is in this Hom set. It's the self map. So I take the identity on some type, and I apply F to that identity, and I get something between F of C1, F of C, and F of C, and it has to equal identity on F of C. So identities go to identities, and composition goes to composition. For any C, C2, C3, FG, F of F circle G equals F of F, circle, semicolon, F of G. That's the rules, and then we're done. So I made sure that identities were preserved and composition was preserved. And if someone gives you that data, then they've given you a functor. Yeah.
Just to summarize, so number 2, what it really means is that there exists a function. For every morphism that already exists,
Yep.
the same morphism exists between the 2.
Yep.
Okay.
Except it's not the same morphism.
Oh,
It's what F did to that morphism. It's kind of F map, if that's right.
Right. Yeah.
Yeah. It maps the morphism to a morphism. So what's your favorite? Does anyone have a functor that they like in Haskell? What? Hate. Okay, list. I was wishing someone would say that. List is a functor from, I'm going to call it from set to set. But you can think of it from Haskell to Haskell or whatever you want. So list acts on, what's an object of set? It's a set. Maybe A is A, B, C. So it has to return a set. As I said, the functors you're used to thinking about, if I'm correct, are functors from your category Haskell to itself. And so list A is a new set. And it's the set whose elements are the empty list, A, B, B, etc. All finite lists. And I'm not giving you a map from ABC to this. That's like a return or a pure or something. This is not a function from here to here. I'm not giving you a map. I'm giving you a new type. Type went to type. It's not a function into it.
The return does generate a new type.
And I didn't give you return.
But pure
Oops.
Pure does generate, it's a natural transformation. It's not part of the function.
So I'm going to give you a functor all empty from set to set.
Pure and F, you don't have those two, you're on function.
Okay, so let me try to fix something. So all empty is going to take any set X and return the empty set. Every set for any A, all empty is going to send it to the empty set. That's a functor, the empty type. Now, does that mean that I give you a function from A to the empty type? I'm not giving you a function from A to the empty type because there is none. So although a return exists, that's going to come later when we talk about natural transformations. The functor part is just the part that takes a set and returns a set. No mapping necessary. All that's necessary is for every object here, I get an object. Every set, I get a set. And if I have a function from A to B, for example, let's say B is 1, 2, and A goes to 1, B goes to 2, and C goes to 2. Then I need a functor from a function from list A to list B. That's what a functor is required to do, is take any object and give an object, take any morphism and get a morphism. And so morphisms in the category of sets are functions, and here's one. And it's going to take any list of A's and return a list of B's. The mapping for objects takes any object in set, which is a set, and returns an object in set.
And you don't need a function for that?
And you don't need a function from the first to the second. It's not, in fact, that wouldn't even make sense if these were different categories. That's why working within Haskell is confusing. Why thinking about functors can be a little bit confusing because you're working in one world, you don't see kind of a bigger picture. There's a little bit like incestuousness to it that kind of makes things a little weird. So, not that there's anything wrong with that. So all I need to do is give you a way to take any list of A's and get a list of B's given this function. I'm going to use fmap, and I'm going to go 1, 2, 2, 2. There is a return type, but that's going to come up in natural transformations, a return function. For all empty, given a map from A to B, I need, on this side of the divide, a map from empty set to empty set. I don't have to give anything because there's exactly one. I'll give the identity. And so I've given, for any morphism in set, I've given a morphism in set. It's just a dumb one. I mean, it says the identity. There's no map across this divide. In list there is, and that's why it's kind of confusing. How about this? So here's another one, times int, taking set to set. So given any set A, I'm going to send it to the, or type A, I'm going to send to the type A times int. Now, is it true that if I had a map from A to B, you could give me some kind of map from A times int to B times int? I had an A int pair, what would my B int pair be?
The identity on int?
I'd do the identity on int, and I'd do f, and the notation I used before, which I don't think is well known to you guys, is f times int or f times identity int. But now, is there a map from A to A times int? Like, is there a return? Yeah, you send it to 53, right? So there's a map here that sends this to A comma 53, and that's my return. But I don't need a return because my return might be different than yours. And there's no universal property I'm guaranteeing about this return. And in fact, if this wasn't set, it was something else. I wouldn't even, an arrow across the divide would be like an arrow from one category to another. Doesn't even make sense. So there isn't necessarily a return type just because you have a functor, or a return function.
You don't need a function to take the object to object. Just conceptually, they need to exist. As long as you have that map that maps over the function.
It's a function from obc to obd, but there's no, it's a type error to ask for a map from the object, from a morphism from this object to its returned object. When they're both Haskell, it's not when they're both the same category, it's not a type error, but it is in general. So maybe it's a good time to take 2 minutes and talk to your neighbor, like see if everyone's understanding this. How are you guys doing?
Well, let's see. One unresolved question that I have maybe is that I'm not sure I totally understand what an object is and whether or not that's like an object is.
It has nothing inside of it. It isn't anything.
Okay.
It's like the behavioral approach to anything. So like, don't think of your implementation. Just think of you as an object with no structure. I don't care about the structure. The structure dictates how you behave and how you interact with other people and things, but it's not. I don't care about how you're doing it. And in the category, the objects are these opaque things, but it's the morphisms that tell you how you behave with respect to other things. So it just takes everyone in this room. You're not. Does that help at all?
Well, I guess like for examples of objects, would that be like natural numbers as an object? Like
Yeah,
a set of
a
natural
set.
numbers
A
as an
set,
object
yeah.
in the category set?
Sets, that's right.
Okay. But like 1, 2, 3, those would be elements of that object.
Yeah, those might be map homs from star. Yeah, I didn't say this, but yeah, those are maps from the terminal set star to the naturals. I don't know if that's at all helpful, but given an element of A, of type A, it's the same thing as giving a map from unit type to A.
Okay, I partly understand that.
If someone wanted to give you an element of type A, they could also give you a function from unit type of type to A, and you just evaluate it on the units.
And is that the way that you normally think of elements? Is functions from
Yeah, everything's all functions. Yeah.
For part A in the subset, is the subscript C, is that a lowercase c or big cursive c?
It's lowercase c.
Lowercase c, okay. All right, well, that makes more sense to me. All right.
Okay, so let's come back. Okay, so any lingering questions? Questions about this? Yeah.
Can you give a non-trivial example of two different categories?
A functor what?
A functor between two different categories, but it's not just like, whatever, make it easy.
Yeah. Okay, so somebody wants an example of a functor between two different categories. So the only categories we have so far are, for every set, we have a discrete category. For every post set, we have that category that is the elements with the less than being the arrows. And for every monoid, we have a category with one object. And we have Haskell and we have set. Those are our category examples so far. So suppose you have two post sets, P and Q. Is this going to be too abstract for what you want?
No.
Okay, you have two post sets regarded as categories. What does that mean? It means that we're thinking of them, the elements of P are going to be the objects in one category. Maybe that's the P. And the objects in Q are going to be the objects of a category. And the morphisms are whether there's a path, including the trivial path. And you can compose because it's transitive, etc. So these are the two post sets regarded as categories. What's a functor F from P to Q in that case? What do the rules of categories say? It says for every object of P, I need an object of Q. So I need to send this to a dot, this to a dot, this to a dot, this to a dot. If I call this A and B, where do you guys want me to send that dot? A. Okay, this one? B. I'll do this one A, and this one? A. Okay. Is this a functor? Well, let's see. I need it to be that for every, so I've given an assignment from objects to objects. For every two objects, I need a function from the hom set in this one to the hom set in this one. So what I've drawn here, this says that this guy's going to A, this guy's going to B, this guy's going to B, this A, this one's going to A. But there is no morphism here from B to A. So this is not going to a hom. It's not going to a function or a morphism. This arrow here doesn't know where to map here. It's going the wrong way. So what I did was illegal, and people told me to do B, and I refused. So this is a functor. It sends objects to objects, and it sends less than to less than. If something's less than, it remains less than. So, and these two properties don't have to actually be checked, because posets are kind of degenerate categories. They're so, because the hom set only has one element or none, it turns out that you don't even need to check these, but you can if you feel like it. So it turns out that this is exactly the same as a functor P to Q is, under this analogy of this regarding, is a monotone map P to Q of posets. That just means it's a function from P to Q that preserves the less than. So preserves less than. So f of P, so P less than or equal to Q implies f of P less than or equal to f of Q. This less than or equal to is P's choice, capital P, P less than or equal to P prime, f of P less than, this is Q's choice. So it's like you have two different systems of privilege or whatever they are, like clearance, and you have a mapping where if you have more clearance in system P, you have more clearance in system Q.
Because we're using posets as the example, are there other examples of what a poset, like, security clearances is one, but what's another example of a poset?
Any tree. The elements are the nodes in the tree, and the morphisms are the can you get from A to B up the tree. Any graph you could regard as a poset by taking the nodes to be the objects, elements of the poset, and the morphisms to be, is there a path from A to B? If so, say it's less than. If not, don't. So this is a functor. Now, does it make sense to say this has a return type? There's no return. It's not even, it doesn't make sense. So as long as your categories are different, you wouldn't make the error of saying is there a return type or not. And that's why working with multiple categories helps you see some things more clearly.
What do you mean by return? Yeah, I'm not even sure.
Oops. Return. So when I say return, I mean return, like, for example, taking A to list A. Or so in a monad, there's like return and a bind. I'm using return like that.
Do you have petitions ever say return?
No.
That's why I don't.
Yeah.
Only Haskellers say return.
Okay. All right. So what do they say in Scala? Or for monads?
Point.
Pure.
Yeah,
Pure.
Pure.
Lift. No. Okay, so it's called the unit. So it wouldn't even make sense to ask, is there, like if you had a translation from some sub-language of Haskell, some domain-specific language or whatever, you tried to use all the same words as Haskell, but you just restricted which ones they can use, to Haskell. That might be a functor from the domain-specific to Haskell. For everything, well, I'm not sure if this is a good idea. So given like Haskell and Scala, there might be a function that takes any Haskell data type to a Scala data type, takes any function written in Haskell and produces a function written in Scala, and make sure that the identity function, when you do this translation, goes to the identity function, and clearly you want programs to compose, and that will be a functor. But you couldn't ask, is there a map from Haskell's int to Scala's int? Because where would that function take, like int is being mapped to int, but that doesn't mean, or int is being mapped to long int or something, who knows? But that doesn't mean that there's some kind of mediating morphism between them because they're in different categories. Yeah.
So you're talking about, when we're talking about monoids, Can you have, so is it a functor to take a pass to a subset of the object of Haskell?
Yeah, yeah. So the third example was monoids. M and N be monoids. We can think of them as categories with one object. Each of them is a category with one object and lots of little things. So what is a functor M to N? Well, it has to send the objects of M to the objects of N. But there is only one object in M. It's this little thing like this. And N is this little thing like that. So the object has to go to the object, but the arrows, every arrow could go to any choice of arrow here. It's just that you would need that the identity arrow has to be sent to the identity arrow. So E to E, like it sends the identity to the identity. And it has to commute with composition. If you take M1 times M2, which is how we wrote composition in this guy, and you apply F to it, it has to equal F of M1 times F of M2. And if you know anything about group theory or monoid theory algebra, which you don't have to, this is exactly what they call a monoid homomorphism. So it's the usual notion. But now we've done it in terms of categories. So
Does it always say liquid? A functor always exists?
There-
Two monos?
yes.
Okay.
So for any two monoids, there's a monoid homomorphism between them. I'll send everything in this to the identity element of this. And then I know if I compose, it'll be the same as composing. But that's a pretty bad, I mean, it's fine, but you threw everything away. So there may be more than that one. But I'm not telling you that there's like a really best one or anything.
Okay.
Yeah.
It's one of the reasons why I'm perhaps harping on this idea that there's like structure that is imposed after implementing like a functor. So it's because we have a Haskell ID. Like, because whenever you go through a functor, you have some residual. You have some sort of structure like list. And you went from A to list A, right?
Yep.
So list is the functor.
But what about all empty? Where I send everything to empty type. Or I send everything to int. What is your... There's no map from... So you have a map A. You have A in Haskell, and then you apply the functor and you get int for some reason. And every function from A to B, whatever, they all go to the identity on int. That doesn't tell you that there's a map from A to int. There's no program from A to int that you're thinking of. So that's where it kind of, yeah. And any other questions? Okay, so there's actually a category called cat. So the objects of cat are all categories. And hom in cat from C to D is a set of functors. And this looks hopelessly abstract maybe, but you can compose functors and there's an identity functor. If you have C and you have C, then there's an identity functor, identity of C. What does it do? The function from obc to obc is the identity function. For any C1 and C2, the function from the hom set C1, C2 to the hom set C1, C2 is the identity function, and everything else works. So there's an identity functor. And also there's a notion of composition of functors. So if I have C to D, a functor, and I have a functor D to E, then I can compose them and get a functor from C to E. What do? You take the objects in C, you apply F, you get an object in D, you apply G, you get an object in E. That's what you do on objects. And on morphisms, you take any C1, C2, you look at the hom set here. F gives you a way to translate any morphism here, like F map it into a morphism here. And then you can F map via G into a morphism here. Am I using that word right? F map? Okay. So then doing that twice, you get an F map from morphisms here to morphisms here. So you can compose functors and you get a category. And what all this stuff is saying is that monoids is a subcategory of cat. Meaning, a monoid, there's a functor from monoids to cat. There's a functor from set to cat. And there's a functor from poset to cat.
You're underlining those. That doesn't mean the natural number thing. You're just
Oops, yeah, no.
right?
Yep.
Cool.
Right. So every set can be regarded as a discrete category. Every monoid can be regarded as a category with one object. And every poset can be regarded as a category where the hom sets are either empty or one element. And when you look at all the maps between sets, the usual functions, like we were talking about before, those will be the functors between the discrete categories. When you look at monoid homomorphisms like we did over there, those are the functors between the categories with one object. And when you look at monotone maps, maps that preserve less than, those are the functors between the categories that they represent. So this is very abstract, but it's also like pretty neat. Yeah.
Monoid there, so set there is all sets.
The category of all sets.
Is that the category of all monoids? Or
This is the category of all monoids.
Not a monoid.
Right.
Category.
Yeah. Yeah.
Not a monoidal category.
Right. Right. So maybe now's another good time to, unless there's a question first. Yeah.
Cat, not the object of the set.
Good question. Set is not an object of set, and cat is not an object of cat. So cat is actually, it's the category of all small, like small enough categories. So what they do is they say, you take some massive set, and you say all my categories, all the objects in them will be in this massive set. All the hom sets will be in this massive set, and everything else, yeah. Then cat will be the set of all categories that can be given a structure inside this massive set. So if you had this way of like if you had this universe, it's called, then cat is a set of all categories that live in that universe. And cat does not live in that universe anymore. It's in like the next level up. So it's a technical point, but sometimes they write like cat sub universe level 1, cat sub universe level 2, and stuff like that. But it's really probably not going to be important. But yeah. I almost erased it because I didn't like it. But okay. Okay, so talk to your neighbor, especially about this, like what I'm writing here, but about anything if you want.
Are those arrows meaning subcategory, or are those morphisms in a category? Or is that isomorphic?
Those are functors.
Those are functors. Which are my morphisms
In cat. Yeah.
Cat is in the morphism, is in the category of cat.
It's in a bigger category called capital C, capital A, capital T. I will try to clarify that. So are we reaching like the upper limit here, or is it okay?
No, I want to get into a little tougher. Like it's not clear to me whether being a subcategory implies
A functor? Okay, that's
all the subcategories or only functors within themselves.
okay.
I'm just wondering.
I'll try to work on that. Yeah.
This last bit here,
Yeah.
the category of sets, monoids, cosets, being isomorphic to the category of
There are
something,
subcategories of
or the
cat.
subcategories of cat. Is this something that we really need to understand and
No.
ingrain to move on, or
No.
can we just say that looks neat and I'll maybe understand it later?
Yeah.
Okay.
Ladder.
All right. Right.
Yeah.
I'm looking at like, any two monads, monoids.
Maybe one more minute?
Get a question about what you're raising.
What?
That little diamond one, just like.
Yeah. Yeah.
They're also an arrow because it's supposed to.
Yes. Yes.
I'm trying to, the thing I'm stuck on is
one good question is that the idea is that you don't need fmap to show that it was a functor all along. Like fmap, which has structure, has information about the structure. It requires a subject. I mean, I don't need a subject though.
I don't grasp.
Like the type class says, oh, I define fmap and therefore it's a functor. It was a functor all along. It had the inherent property of a functor all along. You're using fmap as a proof, right?
Maybe, yeah, maybe. No, the proof would be more like checking that it works. Fmap works with composition and yeah. Okay. So let me try to clarify what's going on. So what's happening right now is we're talking about functors. Any questions about functors? Yeah.
Are there injective and surjective functors?
Yes. A functor could be injective or surjective, and especially the people are interested on the morphism level. They're called faithful and full. So a functor,
Sounds poetic.
a functor f taking c to d, this is actually in my notes. So f taking c to d is called faithful if for all C1, C2, and C, the map, oh, I didn't tell you what an injective function is. Maybe you know already. No?
You did mention on two.
Yeah. If F, and, okay, so let me summarize first. F taking hom C, C1, C2 to hom in D from F of C1 to F of C2 is injective. What does that mean? I.e., if F and G take C1, suppose you have two morphisms in C, from C1 to C2. One's called F and one's called G. And they're such that, ST, all such that F of F and F of G are the same. So under the functor, they look the same. Then they were the same all along. That's what injective means. So it doesn't collapse any two morphisms. And a subcategory can be thought of as a faithful functor that's injective on objects.
Can you draw it as the little bubbles?
Yeah, let's draw it as bubbles. So here's what a subcategory is. You've got a category and another category. And this, let's say this guy is the composition of these two. Then this is a subcategory of this one because I can think of every object in here as an object in here, every object as an object, every morphism as a morphism, and they have the same composition law. So but I can think of that fact that this is a subcategory of this one as a functor. It's kind of like natural numbers can be thought of as integers, but that's a function. They're not just a thinking of, it's a function. If something demands integer type and you give it a natural number, then either you have to give it some way of turning naturals into integers, like take 5 to 5, or your machine is doing that for you. But if you have a strongly typed language, at least in category theory, I need the domain to be the same. So I can regard a subcategory subcategory-ness is the same as a functor that's injective on objects and arrows. By the way, it's called full if this thing is is surjective.
Okay. Surjective and injective shows up all the time, and
it does
in the sense that like injective means it's a one-to-one map, and surjective means that you have full coverage. But is there any other way to really intuitively think of this? Because it shows up everywhere and it's hard to keep track of.
So a functor from Haskell to Haskell would be injective if no two types are sent to the same thing. So is list injective? Well, if I have two different types, are their list types ever going to be the same?
And I'm not even talking about Haskell. I'm just talking
Right.
about category.
Oh.
Yeah.
So the answer is no. And if I have two different maps from A to B, not to you, to what I was saying, if I have two different maps to A to B, could list of them be different? Could they ever be the same map? So you have two functions that take data type A to data type B, and then you apply list to it. You map it over a list. Could they ever give you the same list mapping? Well, the only way is if they were equal to begin with. So this says if they were different, the contrapositive says if they were different to begin with, then they must be different when you apply F. That's often easier for people to understand than if they're the same after you apply F and they were the same all along. Yeah?
Two questions. Sorry, what exactly is surjective?
Surjective means onto. This is not surjective, but this is. Everything in here is hit. And injective means that no two things go to the same place.
Oh, I see.
So this is not injective.
So, just quickly, just to test understanding, what we've been writing about monoids, about how they can actually be categories, that is actually a faithful functor, if not a full functor.
It's a full and faithful functor.
Okay.
Yes. All of these are full and faithful functors. Meaning that, I'm happy about that question. Okay, so the category of categories has as objects categories, and the morphisms are functors. Set, monoid, and poset are things that people could study independently. The category of sets is studied by set theorists. The category of monoids is studied by algebraists, say, and the category of posets is studied by order theorists. But there's a functor from each of those things to cat. You can regard a set as a discrete category, a monoid as a category with one object, and a poset as a category where every Hom set has either 0 or 1 element. When you do that, now you have two ways of thinking about morphisms. You could think about what morphisms were between the sets or between the discrete categories in here. You could think about what they were between two monoids or between the two categories with one object, each having one object, or et cetera. And what this full faithful means that the notion of map that set had is the same as the notion of map that cat had. It's just that cat involves more objects than set or monoid. Or it involves, like set is actually, there's actually a functor from set to poset that looks at a set and returns a discrete poset. The poset with no less thans except the forced ones, the reflexive ones.
How is that surjective if it doesn't map to all the categories?
Right. So, So set to poset is a functor, and poset to cat is a functor, and this is the composition. And now you're asking, why did I say it was full and faithful if not every category is discrete? Or why did I say that this one's also full and faithful if not every category has one object? Because when I wrote this thing, I was talking a bit about surjective at the time, but I didn't say anything about what this did on objects. I didn't say it was surjective on objects, even though I was talking about surjectivity at the time and injectivity. And none of these say that F is surjective on objects. They only say that for any two elements, the Hom sets agree. That's a surjection or an injection onto a one-to-one on Hom set level.
So just to confirm, so full and faithful is only talking about morphisms, or but
Morphisms.
not objects.
Right. It indexes over all objects. It checks something for every two objects. But what it checks is about morphisms only. For every pair of objects in C, it checks something about morphisms between them and morphisms between their image in D.
Is it okay? How does that relate to is it kind of like a bijection?
When it's full and faithful, it's a bijection.
It is a bijection.
So the Hom sets in A, C are bijective or isomorphic to their counterparts in D.
Is there a full name for that?
Fully faithful.
So why are there different names? Why isn't that just a bijection on morphisms?
What?
Why do they come up with full and faithful as
Well, because you have injective and surjective.
But why not
when you do them both.
Injective on morphisms.
Oh, it's longer.
Wait, I'm still
Yeah.
confused about surjective on those set to
Is
cat.
there a picture you can
Monoid to cat.
Yeah.
Cat that aren't mapped, right?
Say again, what's in cat that's not mapped?
Functors between categories that have no.
Yep, that's right. But what this says is that for every 2 objects in C, so for every 2 sets, if I look at the hom set there and I look at the hom set in cat, they'll be the same. Okay. They'll be isomorphic. They'll be bijective. So what is a functor from? What this is saying is you have a set, and you have another set. Then a function between them is a morphism in set, and a functor doesn't make sense between them. It makes sense between these 2 categories, where these are all identities, and these are identities. What I've done here is I've gone from set to cat. So this is my functor, my fully faithful functor that I drew at the top diagonal arrow over there. So here's A, my set. Here's B, a set. Here's discrete category of A, and here's discrete category of B. Discrete means the category where all of the morphisms are identities. So disk, etc. So this is my functor. I take every object in set and I return an object in cat, the discrete category. And I take every morphism in C, in set, and I have to return a functor. Well, on objects, I'm going to take this object to this object, this object, this object, this object to this object. And on morphisms, I need to take identity to identity, so I have no choice. I have to take this to identity, identity, identity. And you can see that to satisfy the properties of being a functor is the same thing as satisfying the properties of being a function. And so there's a isomorphism between hom in set from A to B to hom in cat from discrete category on A to discrete category on B.
Is that a sideways isomorphism?
That's a sideways isomorphism. I knew someone who wrote
Not the real numbers.
who wrote that, and it looked like is, and I thought it was pretty cool. I don't know if they were doing that on purpose.
So what's the value? I mean, like, in essence, are you also saying that these 2 things are isomorphic, but if you don't talk about the objects, if we just talk about the morphisms?
Right.
So it's
That means its set lives inside of cat. Lives inside of cat as the discrete category. You can think of it as a subcategory, or you can think of that but every subcategory you can also think of as a fully faithful functor. I mean, subcategories are equivalent to fully faithful functors. Now, when you find that's false later, make sure you look at the word equivalent, because that's the part I was making it true with. But you can think of a subcategory and a fully faithful functor as meaning basically the same thing.
What's the value of talking about that they're fully faithful? When does this? I mean, I understand.
Well, you can see that cat is housing these 3 categories within it. Fully faithful means that the morphisms are the same, and that, right? So what's an example of a non-fully faithful functor? So list is not. So do you guys think list is full or faithful or neither? It's a functor from set to set or Hask to Hask. Is it full? Is it faithful? Or is it both? Yeah. List taking set to set. I wanted to take, it'll take star to the list, it'll take the set AB to the set including empty list, A, B, AB, BA, AA. That's a set, and that's the functor I mean. It takes a function, and which is the most important part for asking about fully faithful. So is it full? Is it faithful? We're going to be interested in hom sets. So what does list do on hom sets? Given a function from AB to something else, it'll map it over the list. So given a function from A to B, I need a function from list A. Given a function from A to X, I would take a list and I'd turn all the ABCs into XYZs. X1, X2, X3s. I'd map the function over the list. Is that faithful or full is the question. Faithful only both.
It's not
So
full.
the question.
No, it's the fully done from the A's and B's. They're fully mapped over because there's for every A, there's always something you can map to. There's always something in B.
We were talking right. So, is it true? Is there a function from hom in set from A to B or A to X to hom in set from list A to list B? Because we just map it, right? Map over the list. Is it true that if two functions were different, when you map them, they will be different maps from list A to list B?
Yes.
So then it's faithful. Is it true that if I had two different functions from A to B, and I map them over a list, over lists, I will always get two different maps from list A to list B? Is it true that any map from list A to list B is the map of some function from A to B? Why not? Can I come up with a map from list N to list N that's not list A to list N? So I could take every list and map it to length L as the one singleton list. That's a function. I take any list of A's and I give you a list of natural numbers, and all I do is give you the natural number that's the length of this list. And that is certainly not a map, a F map or of a function, because it doesn't preserve length, for example.
What was the question you asked?
The question is it full? Which I erase what that means, but it means that everything in here is hit by something here. So I ask, injective means do every two different things here go to two different things here, or could they collide? And full means is everything here hit by something? And it's not full. There are some maps from list A to list B that are not F map of something, if F map's the right word.
What would be the example of one that's not? Oh, the length.
I did this weird thing, but I could have a map from list A to list B that wasn't. You guys would probably think of it before I could, but
Just take any list to the empty list.
take every list to the empty list. That's not an F map of something. I hope I'm using F map right. So if I keep using the same term wrong, just tell me. Otherwise, I'll just keep using it, and you'll get used to the way I'm using it, I guess. But I was trying to think about a full functor that's from Haskell to Haskell or from set to set. And the only one I thought of, the only interesting one was like, well, I was going to send every type to either empty or unit. I'll send it to empty if it's the empty type, and I'll send it to unit if it's anything else. And that's going to be a full functor. That's the only, pretty much the only one I could think of except constant functors that send everything to something. So I only gave myself one more minute for this part. But I might start, yeah. So let's take a 5-minute break to do whatever you want. No, I have 30 minutes for natural transformations.
This has been really good. I really,
That was
given what